Hi, welcome to the second week of the information theory course. Let me begin by quickly reviewing what we saw last time. So in the first unit, in the first week, the first thing we noted was that we defined information as reduction in uncertainty. So when I give an answer to a question to you, the amount of information I reveal to you is we postulated is equal to the reduction in the uncertainty that you had about the answer before I revealed the answer to you, and the uncertainty that remains after I reveal the answer to you. So to understand this, you can think of a list of guesses that you have for the answer. The size of that list can be thought of as uncertainty that you had before I gave the answer to you, and once I gave the answer to you, maybe you know the answer exactly after that. I revealed the exact answer to you. That reduction in uncertainty is exactly equal to the information I gave to you. Okay, so information is reduction in uncertainty, but then what is uncertainty? So we discussed that to model uncertainty, we have to use some models for the unknown, and we said that throughout this course we'll use probabilistic models for the unknown. So if you remember, we introduced a random variable x which takes values in this set calligraphic x. Throughout we'll use this notation with distribution p of x. So we'll have this notation throughout. P subscript x will denote the distribution of a random variable x. When the random variable itself is clear from the context, we'll omit this subscript. So we can use such probabilistic models to we can use probabilistic definitions like this to model the unknown. And once we have such a model, we would like to make sense of what are our estimates for the unknown. So we discussed these various inequalities, Markov's inequality, Chebyshev inequality. I assume that you have already revised them. And such inequalities were used to obtain estimates for x. So one estimate that I want all of you to remember throughout, I hope you revise this, is that a random variable x is approximately equal to its expected value plus minus some error. If you use Chebyshev's inequality, then we know that this error comes out to be square root of variance, and there's an extra factor in this error here, and this extra factor depends on with what probability do you want this guarantee. So for instance, this statement here says that any random variable x is between its expected value, so this is the expected value, and this is the variance of the random variable. So any random variable x is between its expected value and an interval of length square root of variance with a factor of 1 by root delta when you want these guarantees to hold with probability greater than 1 minus delta. So this is the bound which we derived. In fact, in many cases we can derive a much sharper bound. We didn't see it in the last lecture, but this can be obtained, for instance, using a central limit theorem which we mentioned in the last lecture, that any random variable x is approximately equal to its expected value plus minus square root of its variance, and the dependence on probability of error here is not 1 by delta as Chebyshev inequality suggests. It can be much sharper. It can be log 1 by delta, and this bound is exact for Gaussian random variables, and many random variables have this estimate. So just keep this in mind, that a random variable is equal to its expected value plus minus a margin of error, plus minus an error which is roughly square root of its variance. So this is what we saw the last time, and this week we'll continue with this topic, and we will finally give a formal definition of, not a formal definition, but we'll think of a way of formally handling uncertainty, and we'll see that this uncertainty is related to data compression. And what we will do this week is we'll introduce one of the main quantities of information theory, namely entropy, and we'll see how entropy relates to a measure of, how entropy provides a measure of uncertainty, and how entropy relates to data compression. So I hope you have fun this week.